3.2 The Ideal Diode. This graph shows the voltage and current when the diode is in the forward region. And when we need to find the voltage or current, especially we need to calculate the number in theory, most of the time we don't need to get an exact answer. This is why we can and should use approximations for diode, because its feature is very complex. It's challenging to get an exact number. We'll begin with the simplest approximation, and it is called the ideal diode. The first approximation of diode treats diode as a switch with no voltage involved. First approximation is mainly used for troubleshooting circuit. We already learned the schematic symbol of a diode, and here we see that symbol. The two symbols below that schematic symbol shows the equivalent models. The one on the left is an open switch. This is the model for the diode that's in reverse bias, which means the diode does not conduct. It acts like an open switch. And when the diode is in forward bias, it conducts currents and it's like the switch is closed. Now let's learn how to apply this to solve the diode circuits. For the circuit on the top, the diode is in the forward region, forward bias, and we replace the diode by a closed switch, or simply a wire. For the second circuit below, the diode is in the reverse bias, reverse region, and then we replace the diode by an open switch, or simply remove the diode from the circuit. This is the IV curve for ideal diode. As you can see, there is no current when the voltage is below zero. That's the blue line on the left-hand side of the vertical line. And when the current reaches to 0 amps, suddenly it jumps to infinite. In summary, the first approximation of diodes treat diodes as a switch and no voltage involved. The schematic symbol for first approximation is just the diode symbol. Actually, it's the same symbol used for second and the third approximations. And then in the forward bias, it's like a closed switch. In the reverse bias, it's like an open switch. The diode curve is this one, no current. The current equals to 0 amps if it's in the reverse bias. At 0 amps, it can start to conduct. Therefore, lots of current can flow through it. Again, the first approximation is mainly used for troubleshooting the circuit. Using this method, you can get the answer quickly without going through a very tedious steps to find a more accurate answer. Let's work on example 3.3 on page 63 to enforce the learning. The question is to use ideal diode to calculate the load voltage and the load current in the circuit shown in figure 3-6a. In this figure, we can see that the diode is in the forward bias because the current flows out from the positive terminal of that 10-volt source and it continue flowing, entering to the positive terminal of the diode, the anode, and then exit from its negative terminal, the cathode of the diode, and then continue flowing, go through the load resistor, and then reach to ground. It's in forward bias. Since this is an ideal diode, there is no 0.7 volt drop. The neat voltage equals to 0 volts. So we can replace the diode by a switch or simply a wire. The entire 10 volts is given to the load resistor, the 1 kilo ohm resistor. Therefore, the current equals to V over R. The load current IL equals to VL over VR is 10 volts divided by 1 kilo ohms, and that's 10 milliamps. Example 3-4. We need to calculate the load voltage and the load current in figure 3-6b using an ideal diode. Since this is an ideal diode, we replace the diode by a wire. There is no knee voltage, no 0.7 volt we need to consider. After replacing the diode by a wire, we realize that resistor R2 and the resistor RL are parallel. So we can combine these two resistors using the two parallel resistor formula, and that's 3K times 1K divided by 3K plus 4K. After computing that, equals to 750 ohms. And then we can see that this R1 and then the combined resistor are in series. To find the voltage across the combined parallel resistor portion, in other words, Vp, the voltage measured between point P and the ground, Vp, we can use voltage divider. That is Vs times Rp divided by R1 plus Rp. And that is 32 volts times 750 ohms divided by 6K plus 750 ohms. And after computing the voltage, we know that's 4 volts. 4 volts across that combined parallel branches. So we have 4 volts across the R2, also same 4 volts across the other parallel branch, RL. To find the current that goes through load RL, we can use Ohm's law. Since the voltage across RL is 4 volts, RL is 1 kilo ohms, use 4 volts divided by 1 kilo ohms, and that is 4 milliamps.